Hi developers! Retrieval Augmented Generation, or RAG, is an effective technique used to greatly improve the reliability of your AI models. In this video, we'll learn what RAG is, why it matters, and how we can build our own RAG pipeline from scratch using the Qualcomm AI Inference Suite. RAG solves some of the toughest challenges developers face in building AI. Simply put, if you ask AI a question, and instead of answering based solely on its training data, the AI searches your own dataset and uses that to craft a summarized answer with a reference to the source material. So what makes RAG so powerful? Using a RAG approach makes your model far more dependable. It grounds the model's answers in your documents and datasets, which boosts accuracy and makes responses more relevant. RAG offers strong privacy by keeping your information secure inside your own environment and under your control. Finally, it enhances flexibility because you can update or replace your documents at any time without having to retrain the model. If the model can't find enough information in the dataset, we can even instruct it to say something like, "I don't have enough information to answer," instead of making things up. This prevents hallucinations in the AI output. Now that we have a better idea of what RAG is, let's look at the RAG pipeline. First, we convert the user's query into an embedding, a numerical vector. This lets us search our source data for information that's closest in meaning to what the user is asking. Then, compare the query embedding to an index of document embeddings. This index splits the dataset into chunks. Each chunk is converted into an embedding and then stored so that you can run fast similarity searches. Next, we retrieve a set of the most relevant documents. These are the chunks most similar to the user's question. Finally, we pass both the user's question and the retrieved document snippets into an LLM. The model then generates an answer grounded in those documents. It's important to use the same embedding model when indexing your documents and when generating the embedding vector for each user query. If you later decide to switch to a different embedding model, you'll need to rebuild your index from scratch. Otherwise, you will end up with incorrect similarity search results. Now that we understand the RAG pipeline, let's move on to setting up our environment. To simplify our sample, we have chosen to use a Jupyter Notebook on Google Colab so that you don't need to install anything locally to try it out. All our code will run using the Qualcomm AI Inference Suite on server-scale infrastructure powered by Qualcomm Cloud AI accelerators. You can run the RAG notebook in Jupyter, use the Qualcomm Python SDK and APIs, and let the Qualcomm Cloud AI hardware handle your LLM inference and embedding generation. This makes it easy to prototype and test high-performance AI pipelines from your web browser. Before we get started, you will need to create a server-scale account and download the Imagine SDK wheel file. The Imagine SDK is a Python software development kit that simplifies working with the Qualcomm AI Inference Suite and building Gen AI applications. You will also need to retrieve an API key from your server-scale account. Once you've downloaded the Imagine SDK and your Jupyter Notebook is ready on Google Colab, we can start adding the code to build the RAG pipeline. Open your Jupyter Notebook using Google Colab. Here in this Colab notebook, you can see that we have placeholders for the code that we will write. The beauty of the code that we will build is its simplicity. It's beginner-friendly, it provides a solid foundation that you can later experiment with and refine for production. In the Google Colab notebook, upload your local copy of the Imagine SDK wheel file that you downloaded earlier. Next, we will install the requirements to call the Qualcomm AI Inference Suite. Then install FAISS, Facebook AI Similarity Search, which is a library for searching the similarity between our query and the available data. After running both commands, the SDK and the similarity search library will be ready. Now we can import required libraries. Next, we will set up the API key and the endpoint. You can create the secret credentials in Google Colab by clicking on the key icon in the left side menu. Then add two name-value pairs for API key and endpoint using the values that you got from Surascale. Now, write code to load your stored API key and endpoint. Let's store our endpoint and API key in these variables. The next step is to load some data. We will create some simple data to be used as our ground truth dataset. In a production setting, you'd load files, chunk text, and store embeddings, but this short list will clearly show how the pipeline works. Add the following lines to your notebook. Now run the code, and you can see that the text strings are stored in the documents variable. Next, we will set up our client with the following. Having loaded the documents, we will now turn these documents into embeddings. We'll pick an embedding model from the suite, generate vectors for each document, and then drop those vectors into an FAISS index for fast similarity search. First, let's see which embedding models are installed. Then, run the code, and you can see the embedding model retrieved. We added the 1 in brackets to get the second model in the list since we wanted the larger model. Next, we will create embeddings for our documents. This will print the embedding vectors created for each document. Next, we will convert the format of the embeddings for FAISS to match the expected type and shape. Note that FAISS expects arrays of 32-bit floats and a shape where each vector has the same dimensionality of the float vector as the index. In our case, we get 3, 1024, which corresponds to our 3 embedding vectors, and each have a 1024-dimensional float vector. Now we are ready to create an FAISS index, which is needed to make the similarity search fast. Finally, we are ready to test the query to see if we get the relevant data from the 3 strings we loaded earlier. For our first query, let's enter query equals how can I do AI inference. Then we'll do the embedding for the query using the query, the model, and the data object. Next, we will compare it to the most relevant document. First, we will make sure it's using the same type as what FAISS expects. And we will ensure that it has the expected shape. And then we want the single most similar document to the query. Then we retrieve and display the correct document chunk that we have stored. You see that the index result works well since it returns the first statement from our documents. Now we will try another query. Now, let's call an LLM to have it answer with the provided data. We will take the user's query plus the index lookup and have the LLM answer the question. Here we specify our model, and we also specify that it finds the most relevant answer, and if it cannot, then it returns the statement the data is not in the document set. This ensures that the LLM is only answering from our document set. The retrieved document and the query are the latest from the previous code that we ran. Now, let's get the response. Run the code, and you'll see that the model can answer the question. Let's update the previous question from who is Ray to who is Alice. When we run the query again, you'll notice that the system can't answer. Instead, it returns the message, the data is not in the document set. This is exactly the behavior we expect from a reliable RAG system. So there you have it, a simple, approachable RAG workflow. We just built code that takes documents, embeds them, indexes them, retrieves relevant context, and produces relevant answers grounded in your dataset. There are many exciting next steps you can try on your own. Expand the dataset, experiment with different questions, and adjust guardrails to shape the model's behavior. When you've created your own scenarios, share them with us in the Qualcomm Cloud AI Discord community. And stay tuned for more how-to videos on Qualcomm Cloud AI Inference Suite for more ideas and hands-on examples.